Okay, let me write some stuff. Yeah. Okay. A question for you guys to motivate what we're about to learn today. Out of F and G, if you have no calculator and you have to do it by hand, which one would you rather be plugging the number 2 into? Yeah, of course, everybody. This looks a lot friendlier to plug numbers into than this one. And if you were to ask your computer itself, then your computer would also prefer to plug numbers into here than into here. In fact, your computer does plug numbers into here instead of plugging them into here. Like a question that I get asked a lot about sines and cosines, or I used to, not so much anymore. But people would ask me, like, if I put in sine of 26 into my calculator, how is it doing it? Like, how does it, what formula is it putting in? And the answer is, you'll find out today what the calculator is doing. It's doing this type of thing. So there's something hard about plugging numbers into this function, or into sine functions, or into cosine functions. Transcendental functions is what they're called, like when they're not algebraic like this. There's something hard about that, and even your computer takes a long time to do that. And so it's a lot easier to work with polynomials. And so the question for today is there a way to turn hard functions into easy polynomial functions? Or is there a way to approximate these functions with polynomials? And that's what you'll be learning today. So watch this. This is the function I was working with just now, e to the x. That's what I was asking you guys about. Hard to plug numbers into that. Easy to plug numbers into polynomials. But how am I gonna approximate e to the x with a polynomial? Well, I could start very easy and say, if I want to approximate e to the x at some point, like for example 0 would be the most natural point maybe. If I were to approximate e to the x at some point, maybe I just start off with a constant function that matches it at that point. So at 0, this function e to the x is at 1. So let me see what happens if I approximate this polynomial with the function 1. Okay, there it is. It matches it at 1 point, but it's pretty far off everywhere else. Okay, all right. So maybe I do one step further. Maybe I match the function's value and the function's derivative, the function's slope, at 1. Okay, how am I about to do that? Yeah, okay. E to the x is my original function. Take the derivative of e to the x. Here, e to the x. Derivative, e to the x. Then I want to match this at 0. So plug in 0. E to the 0 equals 1. Okay, all right. So I got, I want to match the function value and the derivative. So what I'm about to do is I'm going to say, okay, if this is going to match the function and the derivative, here's it matching the function. And to match the derivative, I need the simplest function you can think of that has a derivative of 1. You tell me what that would be. Okay, nice. So I'm going to do 1 plus x. Do you agree that if I plug in 0 into here, the function is still going to be 1? Do you agree that if I take the derivative of this, I would just get 1? So I'm matching the function and its derivative. Okay, let's see how close that is. Boom. Okay, now we're getting somewhere. Cool. Good job. Oh, nice, Chelsea. Okay, now we're getting somewhere because look at this blue line is pretty close to this red line around 0, but everywhere else it's pretty far off. So maybe I get one step closer. I match the function, I match the derivative value, and I match the second derivative value at this point 0. So okay, let's try that. Watch this. Oh, hey, this came back. Let's see. Okay, this is my first derivative. Like me trying to match the first derivative. Let me take another derivative. Here's now the second derivative. E to the x again. Trying to match it at 0. So here's me plugging in 0. E to the 0 is 1. So I need to add to this so that the second derivative is 1. Can you guys think of a way to do that? Oh, hey, good job with the over 2. Yep, this, add an x squared. If I left it x squared, then that would be a derivative of 2. So over 2. Okay, very cool. So now, notice I have not ruined any of the previous steps, because if I plug in 0, then this and this will still be 0, so I still get 1. And if I take the first derivative, let's just do it real quick. First derivative in green of this guy would be y prime equals 0 plus 1 plus x. And so if I plug in 0 to this, the derivative is still 1, so I have not ruined any of the previous steps. But if I take the second derivative, then I get the 1 that I wanted to match the original function. Cool, okay, now we're getting somewhere, so here's us adding to our function x squared over 2. That's not that unit. X squared over 2 there. And that's pretty close. That's already, after two derivatives, that's already pretty close. And you can see that if we keep going, it might get closer and closer and closer and closer. So let's do one more until you see the pattern, and then, well, you guys probably already saw it up there. But pretend you hadn't seen that. Let's do one more. I want to now match the function, the derivative, the second derivative, and the third derivative. You guys probably have seen the pattern that I take the third derivative, I'll get e to the x again, meaning I'll get e to the 0, meaning I want the third derivative to be 1. Okay, so here's my function so far. Oh. Okay, how do I add another term so that the third derivative is now 1? X cubed over 3, good job, except almost good job, because watch this. Let me take some derivative. Okay, good job, you guys see it. Yeah, if I take the first derivative, I'd get 0, 1, 1x, and 1x squared. If I take the second derivative, again, notice I have not ruined any of the previous step by adding this because I'm plugging in 0, so all these would cancel and I still get a 1 for every derivative that I want. All right, anyway, second derivative would be 0, 1, and now 2x. Okay, second derivative when I plug in 0 is still 1, everything's good. But now third derivative would be 0 plus 2. That's not what I wanted. So I actually, for every time I take a derivative, this guy's coming down. So I'm multiplying by 3, then by 2, then by 1. So every time I take the derivative, I'm multiplying by another like exponent. Meaning I want to cancel out all those exponents, which is why down here we should have divided by 6. In other words, 3 times 2 times 1. In other words, 3 factorial, if you see it up there. Cool! So here's us checking x cubed over 3 over 3 factorial. Whoa, really close. And you can get that if I keep going, it'll get closer and closer and closer. So here's us for fun. Here's us checking, like after if I did this for 7 rounds. If I did that for 7 rounds, that's pretty close. Not exactly it, because I've only run 7 rounds, but if I were to keep going for forever, it'd get closer. No. But let's see if it can handle like a 50-degree polynomial. Oh, there you go. It's really, it's like exactly on for this whole window. And over here it has trouble like computing that. Eventually it does veer off, but if you keep going forever, it would be exactly that's the idea.
But how can that was not handle it, but our calculators can?
No, the calculators probably do like 10 degree or something. Because like if we go to the 10th one, actually good job, good question. Watch this. Let me call this f of x equal. Let me call this g of x. Here's us approximating e to the x with a 10-degree polynomial. If we take f of 2, like we were saying at first, we get 7 point something. That's close to the exact value. Desmos is doing exactly what we're doing. But if we do g of 2, we get basically the same thing. 7.3889 instead of 90. So maybe Desmos does like a 13 degree or 14 or something.
Yeah. Because based on the graph.
Oh, yeah, we would. But in that case, maybe Desmos does something else, which is actually what's coming up. So, yeah, that's a good question. Notice how far off it is after, like, if I wanted to take e to the negative 10, I would be way far off. And so I'm not sure how your calculators exactly work, but what they might do is instead of approximating e to the x around 0, like we were saying, like match it at 0, match the first derivative at 0, match the second at 0. Instead of doing that, they might match it at negative 10 instead. And do the polynomial there.
Oh.
So that actually leads us to what we're like the first thing on your notes. So let me get out of this. Go to here, yeah. Okay. Right. It says, this says basically what I was saying before, that some functions are easier to work with than others. In other words, polynomials are way easier than other types of functions. That a computer in this section would discover a way to create a polynomial function that approximates any function we want. Yeah, that's what I was saying before. And here is the general way to do it. This is what we were doing before. What we just found was a Maclaurin series, a Maclaurin polynomial for e to the x. And that's because we matched the function, the derivative, etc., around 0. Like we tried to match the function value at 0. Okay, that's called a Maclaurin polynomial. But in general, a Taylor polynomial is one that matches it at any point c. So like at 2 or at 5 or something. And the idea for that is exactly what we just did, except shift over the function by however amount. So like if I'm trying to match it at 2, I would take f of 2 and then f prime of 2 times x minus 2 instead of just x. It'd be x minus 2 to shift it over. Once we do an example, you might see what the idea is after that. But basically, the function value, the derivative, the second derivative will become coefficients. And you multiply by x minus whatever the center is to the degree over the n factorial, just like we just did up there. That's the idea that's coming up. Here's the first example after this question. Correct. Yeah. Yeah, Maclaurin polynomial. A lot of times they're the most common ones that you'll see, just because 0 is such a natural starting point. But yeah, you might get asked like this question, write a Taylor polynomial of degree 3 centered at 2 for this function f that has these properties. Okay, so the idea is, let me basically follow that little formula, or in other words, here's the notation. They say polynomial of degree 3, so let me say P3 of x would equal, okay. And then I'm trying to match the function at 2, so I do 3 plus the negative 4. Here's me matching the derivative value at 2. And that would be times not x, but x minus 2 this time. Yeah, I'm just going to follow that for now, and then I'll show you what the idea is. Plus 7 times x minus 2 squared over 2 factorial, or just 2. I'll put the factorial to be consistent. And then minus 5 x minus 2 to the third over 3 factorial. Cool. Here's the answer. Again, the idea being that if I plug in 2 into here, then this term will be 0, this term will be 0 because 2 minus 2, and this term will be 0 because 2 minus 2. And so I'll match the function value. P of 2 will be exactly f of 2. And then if I try to match the derivative value, take a bunch of derivatives of this, you'd see that you just get 4 plus some stuff with x's in it. But when I plug in 2, I would just get 4 plus 0 plus 0. And so you match the second or the first derivative as well. Take the second derivative, you just get a 7, etc. See what I'm saying? You see the reason for this x minus 2? Okay. If you don't believe me, take 1 or 2 derivatives and you'll be like, oh, I understand that. But that's the motivation behind this. Cool. Okay. There's that one. Here's more examples. If you're generally confused, we're about to do this a bunch more times. It says find the Find the Taylor polynomial of degree n for f of x equals e to the 3x at 2, centered at 2. Okay, so this one is basically what we just did, because it's e to the something. Now, instead of matching the values at 0, we're matching with 2. So I don't know what this would be off the top of my head. So let's get some values, see some patterns, and then we would we'll be able to write the nth degree polynomial. So this would be something like this. Here's some side work. I'm trying to match the function value at 2. That would be e to the 3 times, so e to the 6, whatever that is. Okay, I'm trying to match the first derivative at 2, so that would be f prime of 2 would be, you tell me actually. The 3 to the 6 is what, okay, yeah, because this is a chain rule. E to the 3x is the derivative of the e part times the derivative of the inside is 3. So 3e to the 3x and plug in 2 to get 3e to the 6. Cool. Okay, and then now we'll speed up a little bit. Second derivative would be, you tell me again. Yeah, that would be times another 3. So 9e to the 6. One more. Third derivative would be 27e to the 6. And oh, okay, now I see the pattern. It's e to the 6 times, how would you describe these guys? Coefficient. Nice job. Yeah, this would be 3 to the 0s, 3 to the 1, 3 to the 2, 3 to the 3. So whatever derivative you're on, it's 3 to the that power. Okay, cool. So then the nth degree polynomial would look something like this. Here's me writing it concretely, and then we'll do it in a sum. Nth degree polynomial would be e to the 6 plus 3e to the 6 times the x minus 2, like last time, the x minus 2. Plus 9e to the 6 times x minus 2 squared. Put that over 2 factorial to cancel out when I take derivative. 2 factorial is just 2. You could just write 2 down there, but just to be consistent. Plus, I'll do one more, just to, I'm going to run out of room. 27e to the 6 times x minus 2, x minus 2 to the third now over 3 factorial. And then plus dot, dot, dot till you get to the nth one. In fact, we should get to the nth one because it asks for the degree n. Let me make this small and move it. Here's me getting to the nth one. Nth one would be plus dot, 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 plus the nth one would be, well, we agreed this would be the nth derivative at 2 would be 3 to the n e to the 6th match the other one. So this would be 3 to the n, or sorry, yeah, 3 to the n e to the 6 times x minus 2 to the n over n factorial. Cool. And then again, if you're not seeing why we're doing this, now if you plug in 2 into this function or any of the derivatives of this function, you're going to match the original function at that derivative. Cool. All right. Makes sense. You see where the 3's came from, where the x minus 2's came from. Okay. Nice. On a test, if this was multiple choice, you might see this in sigma notation, which you could write like something like this. It would just be this last term in the sigma. 3 to the n, e to the 6, x minus 2 to the n over n factorial from 1 to n. Except that I just noticed these are n's and we want to go to the nth term, so that could be very confusing. So let me change these to k's so that I can say start at the k equals 0 term and go to the nth term, so that the last thing you plug in is n. So start by plugging in 0 and end by plugging in n. That's why I didn't want n up there. Actually. This would be how you see it in sigma. Cool. All right. Find the Maclaurin polynomial for degree n equals 5 for sine of x. This one, I think you guys should try it. Meaning you should end at the fifth when you get blah 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 x to the fifth. That's when you should stop. So try this one. Maclaurin means, remember, it's centered at 0. So see how far you get in the. Here's a timer so we don't spend too long on it. Hello. What did you do yesterday?
They just got us squared up because Billy was here. So I was helping him. I was doing several other classes.
Oh, okay. Yeah, okay, I get it. I think you were helping in his, like I said, you used to be an IA.
Yeah.
You're doing that IA job now, like he's in.
Yeah.
I get it now.
Yeah, they thought he was going, so they're going to be his job. The one he's doing now.
Yeah.
So then he was here, so it's not.
Really? Nice.
Yeah.
Are you doing the same thing again? Or are you now here in the class?
I'm doing the same thing again.
Oh. So.
Should we get it?
Say sine of 5.
This is right.
No, did you say 5 in there too? Yeah, okay. N equals 5, meaning you should stop when you get to the 5th degree. But it's centered at 0, so you should be getting f of 0, f prime of 0, f double prime of 0. Oh, my bad. That actually makes sense to me.
It looks like putting something. Hey, Chuck, it's on 5 and then.
Yeah. Yeah.
Could you mention?
Yes.
I can. See, I is out of there.
Yeah, it's easier. This should be easier.
Yeah, I just need to go to do, but then it's something.
Yeah.
Oh, yeah, that makes.
Yeah, and you just plug it in because cosine is sine. You want to plug it into the x squared.
But then you can move the expert.
Okay. Okay, all right. So again, I'm trying to approximate sine of x with a polynomial. I want to match the function at 0. I want to match the function derivative at 0. I want to match the second, third, fourth, and fifth derivative at 0. Okay, so here's us doing that. Sine of 0 would have been 0. F prime of 0 would have been cosine of 0, which is 1. F double prime is negative sine of 0, which is 0. F triple prime would be negative cosine of 0, which is negative 1. Fourth degree, or fourth derivative is back to normal sine.
Yeah. That makes more sense.
And then back to 1. And I needed to go to the fifth term. But even if I needed to keep going further, you can see the pattern is 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1. So it could keep going forever. And in fact, if you cheated up there, you might have seen that. But now, okay, let me answer the question. Find the Maclaurin polynomial, okay, of degree 5. That would be e sub 5 of x equals. I need a 0 for the function value plus a 1 for the derivative plus a 0 for the second derivative plus a negative 1. So let me change it back to a minus 1 x to the third over 3 factorial plus a 0 for the fourth plus a 1 for the fifth.
Wouldn't that just be? The zeros, just like,
Yeah, the zeros way would be silly to write, and the ones actually. But just to, do you guys see where this came from? If you didn't get this before, you're good now. You understand the process. Okay, so then, like Jeremy said, this would be a silly way to write it, and more normal way to write it would be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial.
odd numbers on there.
Exactly, yeah. Yeah, that's a good thing to note it today because this will come back in 10.8. Yeah, the sine will have odd numbers only. And if this had asked for cosine, then you can think how that would change this polynomial, but it's pretty similar. Yeah, nice. Cool. All right, so here's our answer for that. Hopefully that makes some sense. I know we got 10 minutes left. I think we got 1 more or 2 more pages. Oh yeah, this one looks crazy, but it's actually not that bad. Oh yes, question.
How do you write the last one as a sum?
Okay, let me not get super deep into it, but you want only the odd numbers to show up. And exactly, and you want to be alternating positive, negative, positive, negative, positive, negative. So alternating series, we know how those go. It's -1 to some power. And then -1 to some power. Let me leave it there. Then x to the odd power. To write odd numbers, you guys may or may not know. Oh, you know it?
2n plus 1.
Good job. 2n plus 1, or you'll see 2n minus 1. I don't know which one.
It depends on which one you start. Like if you start at 0 or
At 0 or 1. Okay, you said 2n plus 1. Let's start at 2n plus 1. Nice. That's how you get odd numbers, because of course, an odd number is just an even number, which is 2n, and then add 1 or subtract 1. And then all over, and again, this power has to match the factorial down here. So if that was 2n plus 1, then this is 2n plus 1 factorial. And then we just have to figure out one thing. Okay, here, I want the x to the first to show up. So then the first thing I would plug in would be 0, so that x to the 0 plus 1 is x to the first. Yes? Okay, so start at 1. Stop at, I want the last thing to be 5 in this particular case. Otherwise, you could keep going forever. Like you could go to infinity.
N equals 1 or n equals 0.
Maybe just equals.
Oh, yeah, sorry. First thing to plug in should be 0. Last thing I should plug in would be 2, because 2 times 2 plus 1 is the 5 that I want to stop at. So 0 to 2. And then I just have to figure out, is it -1 to the n or is it -1 to the n plus 1? And it looks like I want the x to be positive. Meaning when I plug in 0, this should be positive. So I'm good to leave this as negative. Wait, Zach, what the heck? I haven't seen you in the longest. So -1 to the 0 would give me the first power, or the positive that I want to start with. So yeah, kind of intense to write it in sigma notation, but it's a good idea to see it now because you'll see it in a few days. And if you forget, then it's up there. 8:38. Okay, all right. Well, maybe we just do this last one because it looks harder than it is, and then we'll do the next one Thursday. Okay. Watch this. A portion of the graph of f along with the tangent line of f at x equals 2 is shown in the figure below, actually. The region bounded by the graph of f and the x-axis between x and x equals 5 is stated in the figure. Let h be the integral of that. Find the second degree Taylor polynomial for h centered at the x equals 2. That looks intense, but if you take some time to think about it, in fact, if you took 2 minutes to think about it, I think you'd get pretty far. Don't get scared by like, oh man, graph and tangent line and derivative and area, and now this is the integral. Don't get scared by that. Just treat it like all the other ones. Find h of 0, h prime of 0, or sorry, h of 2, h prime of 2, etc., and take it from there. Treat it like the other one. Here's 2. Here's 1 minute because we're short on time.
Is that the graph of that size?
Oh, yeah, they just didn't want to use another F.
Oh, yeah.
This is.
Say that again?
Find the second degree. No, second degree would be raised to the second.
But it was that, right?
I think so far, yeah.
It sounds just like actually.
Wait, that's good, man.
I can't even figure out what page.
Oh, there's some.
Where is it saying?
Why?
All right, just so we don't run out of time and I have to rush, I think you guys were making progress from what I saw. If you're still working, keep working. Just check your answer up here. If you give up, then here's us going through it. I want the Taylor polynomial for h. H is the integral graph, the area so far graph. So again, let me not freak out. Let me treat this just like anything else. I want to match h of 2. H of 2, according to the definition, is just 5 to 2 of f of t. Don't get confused by the t's. They just didn't want to use an x because they'd already used x for the upper bound. This f is still talking about this f. All right. And so how, like, what is this value then? What is it? Negative. What the heck? Why? I see positive. Good job. Good job. Yeah, good catch. This goes from big to small. You want to, 67 over 8 would be if it went small and big. So this would be negative 67 over 8. Good job. All right. There's h of 2. I want h prime of 2 now. What would that be? What about y? Yeah, exactly. H prime is just straight up f. So h prime of 2 is f of 2. F of 2 is the function value at 2, which is 3. Boom, there's h prime. And then h double prime of 2 would be, hopefully you agree, just f prime of 2. But what is that? y. Now that tells me well, you were thinking the right thing. It has everything to do with. It has everything to do with the tangent line, but no, it's not 3. It's not x. It's 1. It's the slope of the tangent line. The slope of that is rise 1 over 1. Rise over 1 is 1 over 1, 1 over 1. So 1. And now you have everything you need. So the polynomial would be p sub 2 of x would be function value plus derivative times x minus 2 to the first over 1 factorial, if you want to be consistent, plus 1 times x minus 2 to the second over 2 factorial. Again, it's silly to write 2 factorial because that's just 2. It's silly to write the 1. But if you want to turn your brain off and just follow the same thing every time, you can do that. Nice, y'all. Good job. We'll do the other one tomorrow. No, not tomorrow. Not tomorrow. No class tomorrow in the morning. Thursday. No.
What? Oh no, did it do it again?
No, but I just know the annotations never came off. Like what I was writing at the beginning of class is still there in red.